Objective 3.7, Composition of Functions. So today we're going to look at yet another way that we can create new functions starting with simpler functions. So all of these lessons in the second half of this chapter, we're looking at ways to create new functions using other functions. Excuse me. So today we want to be able to find the composition of two functions and then state the domain of that composition, of that new function. So let's get started. In example 1, we're given that the f function, f of x, is 3x squared, and we're given that the g function, g of x, is equal to 2x minus 1. Now if I ask you what f of 2 is, hopefully we know from previous experience that this means that we want to take the number 2 and replace it for x in the f function, which means we would be taking 3 times 2 squared, follow order of operations, so 2 squared would be 4, and 3 times 4 would give us 12. So f of 2 would equal 12. If I asked you what g of negative 5 is, same concept. We're going to use the g function, and we're going to replace the x with a negative 5. So that means taking 2 times negative 5 and then minus 1. So a negative 10 minus 1 would give us a negative 11. So what does it mean then when we say we want f of g of x? Well, just like in the cases with our numbers, this g of x is just like this 2. It means that we're going to take the f function and we're going to replace every x in that function with the g of x function. So what does that look like? It looks like this. Our f function originally was 3x squared. So now in place of x, we are putting the entire g of x expression, which was 2x minus 1. When we square 2x minus 1, we get 4x squared minus 4x plus 1. And then we distribute the 3 through to end up with the function 12x squared minus 12x plus 3. We can also do this the other way. We can take g of f of x, which in this case means we're now going to take the g function and replace every x in it with the f function, the 3x squared. So in my 2x minus 1, x gets replaced with the 3x squared, which was the f function. And then we take the 2 times 3x squared to simplify to 6x squared, and we still have the minus 1. So 6x squared minus 1 becomes our new function. Both of these last two examples are what we call compositions. They are new functions being created by putting one function into another function, and that is called a composition of functions. So why don't you try to create a composition using f of x equals 2x squared and g of x equals x minus 4. Try to get both f of g of x and g of f of x to see what you get for new functions. Pause the video and come back when you're ready to check your answers. All right, so in the first case where we have f of g of x, we're taking the x minus 4 of the g function, putting it in place of x in the f function, so that we get 2 times x minus 4 quantity squared We then square that quantity and distribute the 2 to get 2x squared minus 16x plus 32. Excuse me. Sorry guys, I have a little cold today, so hope you don't mind me clearing my throat a couple of times here. For the second one, g of f of x, we're now taking the f function of 2x squared and putting it in for every x in the g function, x minus 4. So the 2x squared replaces the x, we still have the minus 4, and we just simply end up with 2x squared minus 4. Okay, so that's how to create the actual composition, the new function that we're going for. What's a little bit more tricky though is finding the domain of that composition. And the reason it's tricky is because we cannot just go by what the result looks like. Sometimes that works. For example, if we go back to our first example with f of x equals 3x squared and g of x equals 2x minus 1, our f of g of x was 2x squared minus 12x plus 3. Now that function looks like it's a quadratic. And if we only relied on how it looks, then we would say that our domain would be all real numbers. Now, it may be all real numbers, but it may not. These types of problems have what I call hidden characteristics to them. It's kind of like what happens with real parents and real offspring. If you remember, we talked about parent functions being the basis for creating other functions. Well, if you think of those other functions as offspring, so to speak, those offspring have some of the same characteristics that the parent function had. Some characteristics are different, but some are definitely the same. That's what makes them part of the same family of functions. Okay? Well, if we carry that idea a little bit further, I think you would agree with me that there are certain characteristics that offspring can inherit from their parents that are very obvious, and there are certain characteristics that are not so obvious, that you can't tell just by looking at a person. For example, our outward looks can very obviously come from our parents. How many of you have ever been told, oh, you look so much like your mother, or you look so much like your father? Those are the kinds of characteristics that people can tell just by looking at you, that you have inherited certain things from your parents. But there are also certain characteristics that you cannot tell. For example, my father has high blood pressure. Now, can you tell just by looking at me whether I have high blood pressure or not? No, there's no way to tell just by looking at me. Now, thankfully, I do not at this point, but you wouldn't be able to know that just by looking at me. But yet I could have high blood pressure, or I may have a disposition for high blood pressure because of the fact that my father has it, and it may be something that I inherited genetically. Okay, so the same idea kind of happens with these kinds of problems. It is not just about the way our resulting function looks. It's also about the quote-unquote genetics of the functions that created it. So we have to go back and look at the f and g functions to really be able to tell what our domain for our composition is going to be. And I want to try to show you why that is. So I want you to imagine function machines. Okay, this is often a way that teachers will represent the idea of functions, is with what's called function machines. And the idea is that we have certain numbers that will go into a machine. The function itself will act on that and will produce something that comes out of that machine. So for example, in the first slide that we saw, when I put 2 in for x in the f function, I was putting 2 into the f function, the 3 and the squared worked on that 2, and I ended up getting a 12 as something that came out of that function. Okay, so the idea is the function is like a machine that's going to work on a particular value that gets put into that function, and then it's going to produce a particular value that's going to come out of that function. Okay? So using that idea, we can say that there's a basket at the beginning of these two machines that represents the domain of the first function. So in this case, since we are talking about f of g of x, since g is on the inside, that means g becomes the first function. Okay, and then the results of g are what get put into the f function. Okay, so our g function is going to come first. What comes out of g is going to go into f, and then our f function will act on that second. So in this basket right here, we start with the domain of g because g was our first function. So these are the numbers that we would start with and would start putting into the machine. Okay, our other basket is going to represent the numbers, let's back up a step, I got ahead of myself. What comes out of the first machine right here is going to be the range of g. And then what goes into the f of x is going to be the domain of f. Now notice here, those are going to have to be the same numbers, because once it comes out of g, it's going to go directly into f. Okay, so my range of g is what's coming out of this first machine, and my domain of f is what's got to go into the second machine. And then, after f works on it, this basket represents the range of f. This is what's going to come out of my f function when it's all said and done. Okay? So let's say I start with a few numbers in my basket. You can see I have a 1, a 0, a 2, and a -1. Let's go ahead and put 1 into our first machine, into g of x. When we put that in, and g of x works on it, we get a 1 out. That's because my g function, right here, was 2x minus 1. So putting 1 in for x means 2 times x minus 1. That gives me a 1 out. Now that 1 is going to continue and go into the f function, where now f is going to work on it, and I get a 3 out of that. Because now 3 times the 1 for x squared is going to give me 3 as an answer. Okay, and so that 3 is going to go into my range of f basket. So going through the entire sequence of machines here, first the g, then the f, putting a 1 in here ended up giving me a 3 out here overall. Let's see another one. Let's say I want to put 2 in to the g function. What should come out? Well, let's find out. We should get a 3 out because 2 times 2 would be 4, minus 1 would give me 3. So the g function has worked on my value of 2, and it's giving me a 3 out. Now 3 is going to go into the f function, and that's going to give me a 27, because the 3 squared is 9 times another 3 is going to be 27, and now that's going to go into my basket. So here the sequence of machines started out with a 2 and ended up giving me a 27. Now, what you should notice about both of these numbers is if I put them into this equation, I end up with the same answers. So we started out with an x of 1. If I put 1 in here, 1 squared times 12 would be 12. 12 times 1 would be 12, so 12 minus 12 is 0, plus 3 gives me that same 3 I got right there. If I put 2 in, 12 times 4, 2 squared would be 48, minus 12 times 2 would be 24, so that's going to leave me with 24, plus this 3 gives me 27, which is what I got right there. So we can see how this new function that we've created explains the overall sequence of functions here with just one function. Even though it's going through two different machines to get to the answer, this function represents what that overall effect is that takes this first number and ends up giving me these numbers as a result. Okay? Now, the trick is this spot right here. This is where the values of G are going to come out and give me range, but then they have to turn around and become the domain of F as I put them into my second function. So imagine that this cylinder here represents the fact that this section of my machines is enclosed. It's closed off. We cannot get to this section. So if there are values that come out of G of X that are not going to work in F of X, we cannot do anything about it right here. Okay? So it's all about what happens right here. We need to check that what comes out of G as the range of G is actually going to be suitable values to use in the domain of F. If that works, if the range of my first function will be suitable values as the domain in my second function, then everything's good, and whatever my original domain basket was here now becomes the domain of the entire composition. Okay, so what was the domain of G now becomes the domain of my new composition function, as long as this works right here. Now, if this doesn't work right here, this section, if that doesn't work, then we're going to have to fix it. But where we fix it is not here. Where we fix it is over here in the first basket. Whatever numbers were in this basket that are not going to work at this connection point right here, we have to take those numbers out of this first basket, this first domain of the first function. Okay, and only leave numbers in this basket that are going to work all the way through the entire sequence of functions to get to this basket. Okay, so let's take a look at what that looks like algebraically. So we're still talking about the same two functions, f of x being 3x squared and g of x being 2x minus 1. And our composition, f of g of x, is still 12x squared minus 12x plus 3. So the way to check the domain for this new function, this composition function I've created, is to go back and state the domain and range of your two original functions. So in f of x, we're dealing with 3x squared. 3x squared has a domain of all real numbers because it's quadratic, and it has a range of y being greater than or equal to 0, because this is a parabola with a vertex at 0, 0 that has been stretched by a factor of 3. Okay, so this is where you need to be comfortable with what your parent functions are like. and what the domain and range of your parent functions are, and what any kind of transformations might do to that domain and range, so that you can correctly identify the domain and range of your original functions before you try to come up with the domain of your composition. So knowing that f is quadratic, knowing that there's no h or k that's going to move anything around, we know that the domain is going to be all real numbers and the range is going to be y is greater than or equal to 0. For the g function, since it is linear, we know that both domain and range are going to be all real numbers, because that's what happens with all linear functions. So for my composition, because I'm taking f of g of x, and the g of x here is inside of the f function, that means that the g of x function goes first and the f of x function goes second. So when I do my check, I need to check what's coming out of g with what's going into f. So I need to check the range of g to the domain of f. So based on what I just identified a minute ago, the range of g is all real numbers. That's right here. And the domain of f is also all real numbers. So is that going to work? If all real numbers are coming out of g and all real numbers are what we will allow in f as domain numbers, that certainly does work. So what that means then is that original basket that represented the domain of g, that now becomes the domain of the entire composition. So my domain of g takes me back up here and is all real numbers. Those all real numbers just became the domain for the entire composition. Because the middle section does work, my domain of g is now the domain for the entire composition. All right. Let's take a look at that other composition that we had in example 1, where we took g of f of x. We said we got 6x squared minus 1. Now here, it's the f function that's on the inside of the g function. Okay, so that means f function comes first and g function comes second. So in this case, it is the range of f that I need to check with the domain of g. So if we look at the range of f, that's this right here, y is greater than or equal to 0, compared to the domain of g, that's this right here, all real numbers. So that's our comparison now. Now your initial reaction might be, oh no, that doesn't work because they're not the same thing. But they don't need to be the same thing. They need to work. So if my f function is only giving me positive numbers and 0, is that going to work in a domain that's going to allow anything? And the answer is yes, this does actually work. So they don't have to match to work. And we're only interested in, does it work, not does it match. Okay, so the fact that f is only spitting out 0 and positive numbers, that's totally fine in a domain that accepts anything. So again, that means that the domain of f now, since f was my first function, it's now the domain of f that becomes the domain of the composition. So the domain of f was all real numbers. That's now the domain of my new function, which was the composition g of f of x. All right, let's try another one, start to finish, one that we haven't seen before yet. So we've got f of x equal to x to the 1/3, and we've got g of x equal to 8x to the 1/2. What I would recommend before you do any combining or any simplifying or anything else is that you first identify what are the domain and the range of your f function and your g function. So my f function is x to the 1/3 power. That's the same as saying the cubed root of x, and we know from our previous studies that the domain and range of the cube root is all real numbers for both. Okay, so I identify that first. Then I look at my g of x. I'm dealing with 8x to the 1/2. Again, a 1/2 power is the same as square root, so we're dealing with a square root function. There's no h or k to move that, there's just an 8 that's going to stretch it out. So that means that my domain is going to be x greater than or equal to 0, and my range will be y is greater than or equal to 0 as well. Okay? So now that I know what I'm starting with, now let's start putting things together. So first I want to figure out what f of g of x is going to be. That means taking the g of x function and putting it in for x in the f of x function, and then using my laws and properties of exponents to simplify this to end up with 2x to the 1/6 power. So the cubed root of 8 is 2, and then the 1/2 to the 1/3 means I multiply those two to get 1/6 as my exponent. Okay, so that's the new function that I come up with. Now I need to know what the domain of that new function is. So what do I need to check? Well, since the g is the function on the inside, I need to check the range of g with the domain of f. The range of g is y is greater than or equal to 0. The domain of f was all real numbers. So again, does this work? Yes. If my f function will accept anything, the fact that my g function is only giving positives and 0 is totally fine. So this does work, which means my domain for my overall composition is the domain of whatever g was to start with. And my domain of g was right here. X is greater than or equal to 0. So that now becomes the domain of my entire composition. Okay? Now, what if we want g of f of x? So now we're going to put the f of x function inside of the g of x function. And again, using our properties of exponents, we can simplify to 8x to the 1/6. Now I want to check whether the range of f is going to work with the domain of g. So my range of f is all real numbers, and my domain of g is x is greater than or equal to 0. Is this going to work? No, unfortunately it's not. F is going to give us numbers that are positive, negative, anything that you could possibly imagine. But G cannot accept all of those numbers and still work. So when this happens, we have to fix our domain. Normally the domain would have been the original domain of f, that first basket in our illustration. But not all of those numbers actually work. So we have to take out the problem numbers and only have the good numbers left in that first basket that are going to work all the way through the system. So how do I come up with the good numbers? Well, I take the fact that I need my f of x function, which is the first function, to only give me numbers that are greater than or equal to 0. And so that's how I'm going to fix things. I'm literally going to set up a statement that says my f of x function has to be greater than or equal to 0. Well, my f of x function was the x to the 1/3, so I actually put that expression in place of f of x, and then I solve. I cube both sides, and I end up with x being greater than or equal to 0. This new answer now tells me the x values that I have to use in my f function to get the results that will work in my g function. So this answer, this solution set for my x values, that becomes my fixed domain. That's the domain I now want for this composition. Now this isn't going to happen very often at this level, but you need to understand that it does happen, and when it does, this is how we fix things. We take whatever that first function is and we set it up to make the answer fit the domain of the second function, and we solve it from there. Whatever our solution is from that fix, that's what we use as the domain for our composition. All right, why don't you give this a try now after a couple of examples. Use the functions that are given to you here, f of x equals x to the 1/2 and g of x equals 9x squared. You need to find the composition that's indicated, both f of g of x and g of f of x, and you want to find the domain of each one. Pause the video for a moment while you work on this and come back when you're ready to check. All right, so I hope you started by first identifying your domain and your range in each of your functions. F of x is just the square root function, so we have x greater than or equal to 0 and y greater than or equal to 0. Our g of x is a simple quadratic, so our domain is going to be all real numbers, and our range is going to be y is greater than or equal to 0. When we figure out f of g of x, we end up with 3x. We need to check that the range of g will work with the domain of f. As we can see, it does. In both cases, we get numbers greater than or equal to 0, and that's what we can use for the domain. So we're going to use the domain of g as the domain of everything, and that's all real numbers. When we do g of f of x, we end up with 9x as our answer. We're going to check the range of f with the domain of g. F is going to give us y greater than or equal to 0. G is going to accept all real numbers, so that's going to work. And so that means that the original domain of f is now what the domain for the entire composition is. X is greater than or equal to 0. And I want you to notice here, going back to my comment about how it's not always about what it looks, here we ended up with 3x, which is linear. So what would we expect for a domain for linears? All real numbers. That seems to fit. But in g of f of x, we also ended up with a linear, which was 9x. But notice our domain is not all real numbers. Our domain has to be x is greater than or equal to 0 because the characteristic that comes from this square root function has to be part of the characteristic of this 9x. So even though it doesn't look like it has any restriction to it, because of one of the functions it came from, it does still carry this restriction. And if we just go by what it looks like, saying all real numbers for this composition would be wrong and would lose you points. So that's why you have to do these checks. Sometimes it comes out exactly the way we expected, like in f of g of x. But other times it comes out with a bit of a twist. Okay, and the only way you're going to pick that up is if you go through the process of doing this check and working out what your domain is from that check. I want to see this on your paper. I want to see you checking the range of the first function with the domain of the second. I want to see that you have your domain and ranges identified and listed as part of your check, and then what your overall domain is based on your check. If you do not show these steps on your quizzes and tests, you will not get full credit. So as you do your practice, make sure you are practicing it in this way so that when you get to quizzes and tests, it's just an automatic that that's the way you do it. All right, so that's the information you need to complete your Objective 3.7 practice problems in your booklet. If you have any questions about any of this, go back and re-watch sections of the video, ask questions, find other resources that will help you to answer your questions, and don't forget to check your completed practice with the answers posted on Canvas. And especially in this lesson, even though this should be what you're always doing, not only check your answer, but check the way you're showing your work. Make sure you are showing it correctly, that you are showing enough of it, and that you are showing it the way that I'm showing it, because that's what I will expect on your quizzes and tests for full credit. If you have any issues, concerns, or questions, feel free to email me. And that concludes 3.7. We'll see you next time.